this is after the ship was finished, and we went out alongside the apron here, dug a big hole in the ground, filled it full of sawdust chips. Come on, kitty. Come on, you don't need to be up here. Come on. And what we were testing out here really was how the ship's system worked with the tank, and we used the dummy tanks that we had used in our test stand down here at Los Angeles. And you can see all these bundles of wires hanging on here. They're all coming from different strain gauged areas on this beam, and we're going into amplifiers and into data recorders. And some of these, of course, are control wires going to the breeches, the housings where the cartridges are sitting right there on the back of the store. This thing here is the outboard sway brace on the right-hand side, and on the left-hand side is sway brace that you see on the photographs of the external tanks.
How come the external tanks were of different weights? Was there ever any try to weight one? So I know the fuels and stuff were different weights.
Fuels were different weights, and then since you don't require as much of the liquid oxygen as you do of the anhydrous ammonia, then the whole forward end of the LOX tank had big pressure vessels inside that were storing helium that was under pressure that was used to drive the fuel out of the tanks and upgrade the fuel system in the rear. It wasn't done with pumps, it was done with pressurized tanks, so that pressure from those tanks had to be forced into the liquid oxygen tank, transferred across ships to the anhydrous ammonia tank on the other side, and that pressure drove the fuel up out of the tanks through big long feed tubes and up into the ship system. Now then, that accounts for the differences in the empty weights of the tanks, and then there's some difference in the full weight of the tank too.
Was there any attempt, or did they just feel that it was better just to have that asymmetrical weight on there? Was there an attempt to try to weight them?
No. To ballast them in some way?
Yeah.
Do you have other photographs of the...
I think this is the only one I've got of the test phase with the tanks. I've got a lot of shots of the tanks and stuff, but this is the one with that fixture on it.
Okay. There's undoubtedly going to be a lot of shuttling back and forth here as we move from subject to subject. Since we were talking about that beam, I was going to try and find some of the pictures of the test stand. There's looking at one end of the beam. This is clear out on the outside here. You can see big plywood sidewalls, a huge, great big box with plywood sidewalls, plywood ends on it that ran the entire length of the test stand. The box probably stood 5 feet deep. We'd have to crawl up over it and down inside. When I wanted to look down inside, we were dropping with them maybe from an 18-foot high test fixture. Okay. And you can see some of the bundles of instrumentation wires coming out of there that went over to our carrier amplifiers, and from the carrier amplifiers onto the recording. We would be recording 12 channels of data at any one time, and the data was set up so we could switch from area to area along the beam, or area to area in the explosive system, area to area in the mounting points in the test stand, which would be equivalent to the mounting points in the aircraft, so that we could monitor all the loads. So,
was all the testing done by North American, or did the Air Force get involved in the testing of it, or did they just sort of sit back and wait till the E-2 was in place?
This is a part of our contractual agreement, is to do all the design and testing of the system and deliver them totally working package. But we couldn't afford to build additional tanks for the tests, so we built these test beams that had exactly the same dynamics, the same weights, the same spring constant throughout their length, the same mass moments of inertia, so that they behave exactly like they would on the aircraft. And not only did we do the ejecting of the weights, we also loaded the tank just as it would be at different points of the flight. In other words, the aerodynamic loads that would be acting on the tank, depending on whether the tanks had to be ejected right at the time it launched off. In other words, if there was no light up, you'd have to eject the tanks immediately. If we had to eject partway into the mission, we were duplicating those loads, or if he was ejecting at the max flight envelope, the Mach 2.1, where the tanks were supposed to come off, whatever the aerodynamic loads were on the tanks, we simulated those in our testing too, so that the entire test system was functioning exactly like a flying aircraft. Now, even that went through phases. In other words, we had to test out, starting out by testing out the cartridges and cells, starting out by testing out the ignition system in the cartridges, the ducting of the propellant gases over the long distance. See, the tanks were something like 19 feet long. So, since one of the thrusters was the back end, one of the thrusters was the forward end, and the cartridges were located a few feet back from the front end, then we were ducting gases forward as well as backward over that tremendous length. We had to check out the velocity of the gases, the pressure of the gases, and how much pressure was left after the gases had traveled that distance, what the effect of cooling was to the propellant gases by the time they reached the head of the pistons to initiate thrust, to keep the tank clear of the ship. So that was the purpose of the test stand and these test beams.
How many sets of beams were there?
Just two of them. The two that are hitched on the airplane there. The one that we made initially, that we're using our test stand, that was the only one that we constructed for it. And then, prior to doing that test, after we had taken the aircraft to Edwards, after the complete rebuilding the aircraft, then we manufactured the second dummy beam and took it up there and did testing of the the ship in the ground. This is one of the things that happened during an overload charge. We wanted to see if there's any failure in the system, depending on how much of the gun gases went to the rear piston, how much went to the forward piston. If one of the lock points should fail to open up, what would happen to the structure? And see that they collapsed. In other words, the force of the piston here was high enough to cripple the beam. You can see attached to the beam by itself represented just the empty structure of the tank. These huge, big Kirksite slabs on here were added to provide the equivalent weights of fuel at various compartments throughout the tank. And this happens to be an ejection that's occurred from the upper top of the test stand here down into this big plywood catch box. And in the bottom of the catch box we have these huge fluffed up balls of heavy oiled canvas. By taking those big wads of canvas and fluffing them all up and making them into big loose balls that way, it acted as a very good decelerating medium when this thing would come flying out of this test stand and strike the ground. By starting to compress on all that heavy canvas fabric and blowing that air out of there, acted as a natural decelerator to take off the impact of that thing actually bashing into the ground. When we were up there at Edwards with that other photograph.
These are all in North America?
Yep. This is all right here at our facility at LAD. When we were up there at Edwards, I had that thing full of we were using sawdust chips and canvas. Had a layer probably 2.5, 3 feet thick. Great big redwood sawdust chips and then fluffed up balls of canvas.
How deep is the pit?
Well, it was probably 6 feet deep. In other words, we were able to, by filling that part way up with redwood and then with these big lumpy balls of fluffed up canvas, we were able to get it up pretty near the ship where we could get in with using the high-speed cameras running on the inside, get the photographs of the tank being ejected off the wing and then coming down and then settling in that canvas and then that all compressing down into the bottom of the test stand.
Was the aircraft actually set? It was set down on the ground, I take it? It wasn't hanging in the air or anything like this. They were just setting it in.
It was setting down on the ground, setting on the skids here at the back end and setting on this platform, the nose gear setting on this platform.
Was it actually just sitting there, or did they have it bolted down so there wasn't any?
It wasn't bolted down, but it was tied down with cables.
Didn't get a big backlash.
Yeah, well, the thing is that whatever, anytime you try to, like separating a bullet out of a gun or blowing any two things apart, it's an action-reaction principle where the load is the same in both directions. Now, with 30,000 pounds ejection force on here, we were developing enough force in forcing these tanks off here to lift the bird off the ground. So it was cabled down. And it was cabled down using the jack points on the plane. The jack points on the plane are structurally sound enough that you could set the airplane on jacks, tie it down on those jacks, and it can resist all kinds of loads. Can you get on? I'm going to lock you in the back room shortly. think that those are going to be all. Oh, okay. Here's the same sequence as that picture there.
That's what I've got a picture of this, but it's from further away, and I didn't even notice that it had the weights on there. The
Don
beans.
Peterson, a photographer named Don Peterson, went up there with me when we were doing this program, and he set up all the high-speed cameras. These we had this thing covered from a number of different angles, in from the back, directly head-on, from the front, high-speed cameras standing off here to the sides, and you can see pull cables on here. You see these big jack towers standing up here? These cables, okay, we're simulating those same aerodynamic loads that we did in the ground test stand down at North American. We simulated those same flight loads, even with the thing tied down here on the ground. And you can see that the aircraft is setting out on its skids on this pad here and the pit on the nose gear, but then it's tied down below the jack points in the hard face areas in the concrete. And of course, someplace in these photographs there, the instrumentation, I don't know where I'm looking for right now, but the instrumentation truck has to be sitting there someplace. I don't see it right now. But the purposes of these big grid boards that you see here in the back, these grids are set up here every 2 inches down along here with a velocity measuring device, a point in between each of those grids. And this was done at each end. We'd have 3 high-speed cameras, one high-speed camera looking at the front end of the tank moving down along this grid board, one high-speed tank looking at the back end of the tank at its grid board, and one overall camera looking at the total picture. So you get the idea of pitch, but we would know exactly at what velocity this thing is separated. And that was done from a camera standpoint. And from an instrumentation standpoint, we had what we call a velocity harp. It's a long sheet of formica with a row of just those thumb down contacts that you slide wire in and button them down. Okay, up one side of the board here and down the other side of the board here, and then in between those things. We'd take just regular, drafting lead like you put in your drawing pencil, just plain graphite lead goes in between each of these things. And then with a signal coming out of there and coming out of here, all we've got to do as soon as that tank has been ejected past this thing and a little Donecker sticking out of the side of the tank, as soon as it starts breaking these leads, then we start changing unknown resistance across here, which on our oscilloscope trace or our oscillograph trace coming in recorder gives us a whole series of traces like that. So it starts out, you're reading time in this direction and magnitude of resistance in this other direction. Starts out real slow and then gets faster and faster and faster as the velocity builds up. So we knew what the velocity was exactly at the center, at the CG of the tank. We knew exactly what the velocity was on either end of the tank. So we were measuring pitch as well.
I presume that it was designed for a nose pitch down.
Absolutely. That's the way the various components on the tank work. That's why we have that big rocket motor.
What kind of velocity was the tank ejected at? just an approximation.
Let me think about it a while,
Okay.
and let me see if I don't have a copy of my report document back there someplace. That, a fellow by the name of Leonard Gaines. I don't know if you've come across Leonard Gaines.
No, I haven't.
Well, this is my wife, Donna.
Hi.
How you doing?
Nice to meet you.
And this is Larry.
Hi, Larry.
Evans. Leonard Gaines was the aerodynamicist for the X-15 project group, and it was up to Leonard to determine what the safe separation velocity had to be in the full, the partially full, and the empty condition, based on various speeds that the aircraft would get itself up to at those times, and what kind of dynamic forces were being felt by the bird. So it was up to Leonard through a series of wind tunnel tests in our supersonic wind tunnel there at North American to determine what those velocities had to be through analysis and through models that were made and injected there in the wind tunnel. And then that gave us the design parameters for the tank structure itself, and what kind of loads would be imparted into the tank structure to achieve those separation velocities. And it told us what our thrusting mechanism had to look like, what our pistons would look like, how large a diameter on the head of the piston would have to be, what the length of the piston shaft would have to be, how long a time period the force stroke had to be taking place. And that was all previously done by Leonard in the wind tunnel. I just wanted to make a quick check and see if I had any more testing. I don't. So I guess any of the ground testing procedures we only have what you see here between the two.
So it was your main thing was just with the tanks, or did you have anything else to do with the A2?
Tanks.
Or just mainly the
Tank design of the cartridge injecting system, getting the drawings and release EOs into the shop, getting parts made, getting the test beams made, getting the test stand set up, doing the ground testing, and at the same time following the construction of the tanks and the fabricating departments in the shop, and then eventually marrying the whole works at NASA, getting the bird, the test beam, the tanks up there, and then getting ready every time we had a flight, getting the tanks onto the aircraft, getting going with the rest of the crew out to the run-up stand, doing the engine run-up on the ground run-up stand at the edge of the wake bed. And then the next morning, servicing the aircraft before flight, and then finding and recovering the tanks up at Mud Lake, and then bringing them back down to LAD to be rebuilt. The idea was to build a reusable tank, which by very simplest refurbishing would make it ready for next flight.
How successful was the refurbishment? Were they usually recovered pretty well intact?
Yeah. There was only one last one. But the other tanks were used over and over. And of course, it would depend from time to time how extensive the damage was would depend on how well the recovery system worked. The one tank that we never could use again was totally demolished. One of the parts that we got from Highshare made some of the explosive components for us. And on the very first flight, one of those Highshare components failed, and we lost the tank. I think I've got I was going through this here. I think I saw this picture.
How long was the total design effort then?
Well, I couldn't tell you right now, but it wouldn't take too long to calculate about how long it took us to do it. One of these, this is the equipment. This is a brochure that was put out by Highshare, showing their items that they had designed for our system, and this is just some of their advertising material we're kicking on. But this component right here, this is the forward bulkhead on the end of the tank. This is the drogue chute or the main recovery chute that's enclosed in this part of the nose cone on the tank. The drogue chute that stabilized the tank once it was first ejected was in this other compartment right here, and the canister was fired out of there. And then on the very first drop, there was a failure of one of these thrusters in here to operate correctly, and the nose cone never came off, so the main chute couldn't be deployed. And we lost that first tank. But very quick on the spot investigation we immediately determined what part had failed. And Highshare made a very rapid redesign of the part, rebuilt all the parts that had already been delivered to us for the rest of the tanks, and we never had a failure of the component again. That's that tank there. And that's working back to the desert. And I was just going over to the tank at the time of the recovery, and Chopper was coming in. This is the tank that we shot from the other side of the aircraft right at the same drop point, and it came down unsatisfactory. So we lost one of the tanks immediately on that, but we had successful tanks made, so we had the loss of one tank was not a great problem. You can see here is the way the tank is designed. The main recovery chute sits right here in this compartment. Right in here in the belly, right here in this compartment here, is a smaller diameter drogue chute. It's stuffed up in here, and it is also fired out by a ballistic device. It's a slug that sits in the cartridge chamber with a cartridge housed on the back end of it, and when that's ignited, that thing is blown out of here like a mortar round would be. And after it flies out here 10 or 15 feet, it starts pulling on a great big nylon cord that jerks the drogue chute out of this compartment. And this thing first comes off the ship. They're blown off the ship at an angle normal to that side frame on the ship. The rocket motor up on the top surface ignited at the same time, which gives it this rotational moment away from the bird. And as they start to tumble, that drogue is fired. By that time, the tanks are in this kind of a mode. That drogue is fired out, and as soon as that drogue chute deploys, the tank immediately whips around, and so it's falling right straight down vertically. And then inside this same compartment here in the tank is an aneroid switch, an altitude sensing switch. And when you get the tanks down low enough to the ground, the altitude sensing switch closes, which blows off these two little igniters and thrusters here that kick that nose cone off of there, which is pulling on the ribbon, and the nose cone flies away. Then it deploys the main big 48-foot diameter chute, which lowers the thing down to the ground. Now then, the thing is coming down to the ground then with its ass end downward. And what happens on the back end of the tank are a couple of impact switches. And you'll have to bear with me digging through this stack and not knowing what we'll be talking about at first. I didn't bother to try to arrange these in any particular order here. As long as we're talking about tanks, we'll have a look at some of these structural things on the tanks. Pictures better now, because we furnished them with the picture there and just cropped it away here and here are two switches sitting in there with little with a micro switch plunger on the unit, and when this thing is being lowered down by this main chute, then this is the part right here that impacts first on the surface of the desert. And in crushing these little housings right here, then it compresses that micro switch inside, which shoots a signal back up this lead pipe going up to the front end, and pulls a pin out of the main line on the drone on the recovery chute, so the recovery chute immediately turns loose and just drifts out across the ground. Now then, while we're looking at this back end, if this thing was to attempt to be dropped with the parachute system in full condition, the weight would be so heavy that the parachute couldn't possibly support it. So at that time that signal went to that drogue chute to be mortared out of that forward compartment up there, another signal came back to this and this cartridge right here through this wire bundle coming right out here. And these two cartridges going off, this bolt that you see through here is a piston, and it blows those two rings open, and that allows this lid over here to pop out of there. So it opens up immediately in a 6-inch hole and back into that tank. As soon as that drogue chute rights that tank, any residual fuel that's inside gushes out the bottom of that hole, because it had some initial downward velocity, and when that chute rights it on, it just spews out the bottom. These two cables that you see right here and here are merely to keep this unit together so that these don't go flying off into space. Actually, this doesn't go flying away either. On the inside of this is a long fastener that comes back and just jerks against a collar that's inside. So, but it's open all the way around like that, so it goes in fuel to splash out there. Now then, we found after the first couple of drops that really these things weren't quite sensitive enough. So we made this housing a little bit longer and put a tickler wire out here, about a 12-inch long piece of wire. So as that thing came down close to the ground, no matter how the wind was catching it, well, our problems were some windy days down in the desert. There'd be, nice air up above where the ship was flying, and so if they get off a good ejection up there, but come down on the desert and some of the side winds catch it, the thing might be, even though it's coming down on the chute in this general direction, the wind velocity sideways is high enough, it'd strike on the side rather than hitting these things directly. So by putting the long tickler out the bottom, it would immediately compress that micro switch up one side and detonate these charges, and which would cut loose the main chute in the front end. What it does, it doesn't cut loose both straps on the main chute. It just turns loose one, so that then the sack on the chute immediately spoils both. So much for that system and the way it worked. This is the outboard sway brace that you saw in that one photograph that you had here. It was bearing up against a jack point in the side of the ship. On the inboard side, since the load would be higher on that side because the tank is setting off at an angle like this, the dead weight of the tank tries to collapse it down like this. We couldn't find any one point that was strong enough to take that load, so we had to deliver the load out over two frames that were in that side fairing along there. And this is simply a swivel point right here, so the thing was more or less self-aligning as it would come up. This is the big thruster housing and the piston in the rear end of the tank. And there was one of these at the forward end. And then in the center portion of the tank, we had the pressurized lines. I told you, remember, in the liquid oxygen tank? This is the portion here where this reflective tape is, where the liquid oxygen was held. This compartment here had the three huge pressurized vessels on them. It had the helium gas that was used to drive, to expel the fuel out of these tanks. This is the helium gas transfer line here coming into this tank. And this right here is the big fuel transfer line, big 5.5-inch line that made it up into the fairing in the ship where we built in that 29-inch stretch section. See, the burden had to be stretched 29 inches to accommodate all these big fuel transfer tubes and to accommodate the structure that was to take out the drag load in the tank. You realize anytime you're trying to transport anything through the air, you have the download of the thing itself, you have their roll and yaw loads in it, and the drag load of just trying to move the thing forward, and also the arresting load if suddenly your aircraft decides to stop, and then you've got an arresting load. Okay, that was all, that drag load and arresting load is taken out by this big steel pin that you see sticking up here. That goes into a hardback on top of the tank, a very rigid section in the center of the tank, and that had to go up into that 29-inch strut section. There was a hard frame up in there for that pin to go into. So that 29-inch stretch, there was really a lot of things going on in there. It simply wasn't to make the plane larger. We had to do it to accommodate the flight loads that had to go through there. We had to do it to accommodate these big fuel lines going through there. We had to do it to accommodate the helium gas coming from the LOX tank over to the NH3 tank. That kind of thing. And then continuing forward up the tank, then we have the rear end of the rocket motor housing. The rocket motor sat over on that other side of the tank. I don't think in this shot there isn't a rocket tube actually sitting in there, but this is the rear end of the housing. And then immediately forward of that, these are the igniter heads, which is this shot right here. The igniter wires coming to the igniter end. This shows one of the chambers open and the igniter wires exposed. This shows the other cartridge holder closed, the way this is normally secured prior to flight. Now then, these long tubes going back here are the high pressure tubes carrying the gases generated by these cartridges back, all the way back to the back end of the tank to the ejector piston that we saw here. And the gases go down inside this housing where this ejector is into the base of the ejector so that they blow the piston in this direction. In other words, the piston is pushing against the aircraft. The piston will normally starts out really statically against the aircraft, and it's the cylinder housing being pushed off the cylinder rather than it is the piston being thrust out of the cylinder, because your airplane doesn't move. It's the cylinder being pushed away from around the head of the piston that's pushing the tank structure away. And then going forward are the other set of lines going up to the ejector on the front end of the tank. These are tanks away sensing devices here. This was a hole that goes through this bracket, actuating these two safety switches right here and holding the tanks away lever down. All these switches are simply safety switches to the various igniter systems throughout the tank, so nothing can work, nothing's even armed until this pin is pulled. And when that pin is pulled, this tank's away lever here raises just slightly until it touches the bottom of the fuselage. And then after ignition takes place in the cartridge housings and the store moves away, then that lever flies open here and arms everything else in the system so that the other explosives will occur in their normal sequence as the event progresses.
This is the drogue chute housing down here?
Yeah, this is the drogue chute housing right here. Even the door gets secured into the end of the mortar, so as the mortar fires out of here, it takes the door out of there with it, and after the mortar extends out there, the slug extends out there about 15 feet, jerks the very tightly compressed chute. I think that, if I recall correctly, was about a 15-foot diameter nylon chute, and it was the type that had a series of goers all the way around the chute, so it was a real high velocity, high drag loads on the chute. If you'd had a solid chute, velocity sometimes would have really ripped to pieces.
Did the drag chute get fired off when the main chute came out, or did it stay with it?
It stays with it.
It does. Yeah.
I don't know if anybody has shown you any of the other movies. I've got this little roll of stuff here that I shot of my own. But in some of that film that's shot from those big Scania cameras, and the film that was shot by our camera crew from our space division. Our space division furnished a huge, big television camera, and we took live TV pictures. At the same time, we had a high-speed 16mm telephoto camera sitting next to it, and then on the range we had the big 120-inch scanning cameras that we're watching. And you can see all this stuff occurring as it comes down through the air.
I haven't seen any of this at all.
Yeah. This is the forward ejector here, and from those same cartridge housings that we were looking at in this other view, there are two lines, two of those big stainless steel gas lines coming down into this compartment and up into the bottom of this piston. This is the big piston that forces off the planet. And this is merely an access door here on the bottom to get up into that piston. It has an unlocking and locking device in it. A little shear pin in there that has to be put in. That pin is sheared. When the gases from the initial explosion go in there, the thing has to shear the pin, unlock itself, and separate off the bird. Feel free to stop and hit any time if we're not. If we're not hitting this.
Okay. Well, you mentioned before that you were part of the team that was responsible for actually setting up the tanks and for each flight. So North American was responsible for doing the tanks on every flight. It wasn't something that was turned over to NASA.
Well, responsible. I should say overseeing. No, it was NASA personnel.
Okay.
NASA crew chief and crew. We were there. Since it's really not one of a kind thing, but it's almost one of a kind thing. We were bending over backwards to get assistance that we could throughout the program. They'd have transfer of personnel up there. There were a couple of mechanics that went all the way through the program, but you'd go back. So sometimes we were briefing a new mechanic for the first time. So we were always there. No, as far as physical labor and manhandling the equipment, they were doing all that. Let's see, we've already. This is simply a photograph just to show what was used as a lifting device for taking these things out of packing crates, putting them on the dollies, and getting them over to the bird. They're just what we call an age item, or a GHE, aircraft ground equipment, or GHE ground handling equipment. So they're just an age device.
I used a lot of age equipment and stuff when I was in the Air Force.
Yeah. Okay.
Yeah.
And it ends up being a very expensive part of the of the contract dollars. It's amazing how much. Be a little better first. This is simply a photograph of the LOX tank showing the components on the top of that. There's that drag load and the resting load pin sticking up out of it. It has to go up into the center hard point in the X-15 in that stretch section. This fairing is rapidly removable right here and here, so we're doing the mating to the aircraft. Why the mechanics can work back in here. They have to make up this line, they have to make up these lines, they have to make up the heating lines as they come up. Everything has to be connected and screwed into place.
Was there ever any talk of doing this kind of a thing with any other aircraft except for one? Was that all they ever intended on doing, or did they ever think they might do this to a second aircraft?
No, it was only, as far as we only had one aircraft available to us, and the only reason was that part of the outgrowth of rebuilding that thing after McKay rolled over on it was to, it seemed like a good idea. Now then, as far as another system being designed like it, several years after we got into the B-1 project, and then the Space Division started Space Shuttle, they took this whole system, ran it through a bank of computers, and scaled everything up. Chutes got scaled up, the type of structure got scaled up, the monocoque structure of the tanks, the ejection system got scaled up, the cartridge size got scaled up. This is basically the same system that's on the big center section and the two engines in the space shuttle right now. It's the same system. It's greatly enlarged.
Yes, slightly enlarged.
They used all of our data and simply scaled up and built what parts. This is the 29-inch stretch section. This is the bird while it's back down the LAD being rebuilt. These are some of the tanks out of the inside of the bird.
Were those extras, or those ones that are still yet to be put back inside?
In this particular case, I couldn't tell. At the point on the side fairing at the back and the front, and on the other side of the ship, or front and back, and front and back here. This is the thing that's up inside the bird. Now then, I don't know whether you noticed it when you were at right path, when you looked at the Dash 2 bird.
I remember seeing that.
You should have seen this little clamshell door.
Yes.
Seeing it. Okay.
I was wondering. In fact, I took close-ups of those because I wanted to find out what those are.
Okay.
Yeah.
We'll go into that right now.
Okay.
This is what the unit looked like in the bird, with a little access flapper door open. This has to be forward because all doors,
Yeah.
you hinge them on the front, so that if the hinge the spring fails, well, the
They'll have to open
airstreams
up,
keep
yeah.
the airstreams keep. Okay, now up inside the aircraft, in this hard frame right here, was an assembly that looked like this. This thing has a great big thread on here that rotates up into the aircraft structure. And completely assembled, it has these two hooks up inside, right here and here. These hooks have these two rollers right here and right here, which is that roller you see there, and the other roller right there. And these pins going through these rollers and through this hook, keeping it in place. Okay, now then, those two things in turn fit in this body, with one of those hooks swinging out that way, one of the hooks swinging out the other side, and then these two big pins right here going through this hole and through that hole right there and right there. This in turn being able to pivot in this body here on this big pin going through this fitting right here. So that this thing actually jostles back and forth around that pin there. We'll get in just a few minutes as to why that does that. Okay, now then, the piece in the tank, the ejector where the gun gases come in, down in here to the bottom of this cylinder cap. This is the cylinder housing right here. This is the piece that we saw sticking out of the tops of these tanks. And that particular tank doesn't have. But you remember, we saw that big cylindrical.
Yeah.
Yeah. Okay. Yeah. Right here. Right there.
Yeah.
Right. This is the piece here then that goes up inside the aircraft. And as it goes up inside the aircraft, it's coming. You notice it has a hole right here in top, and it's coming right up over that Donecker sticking down there like that. These two hooks are collapsed inward to one another at the time that's done. As you come up into it, then those two things get spread apart. Those two hooks get forced apart, and this thing right here has a shoulder in the top. So those two hooks are coming right in underneath that shoulder, like that. That's the thing that takes the download in that tank in that direction is being reacted by these hooks and shear in this pin right here and here. Those two pins take their load into this housing, which in turn puts its load in shear in this pin. Well, actually double shear, because there's a shear face here and a shear face over here on the other side. That pin there in turn is going through this hole, transferring that load into these big threads, which is right there into the aircraft structure. Okay, now then, the way this thing works. Even though these pictures shown here are the forward piston and the aft piston, they both work in the same manner. The back piston is a little smaller because we don't require the amount of ejection force on the back end of the tank as required on the front end of the tank. You'll notice that there's two pistons here actually. One of these pistons slides down inside the other piston. And then the larger piston is put inside this housing here, and the cap is screwed on it, which means this end is going down through and out this end of this thing right here. Okay, this is the big thrusting piston that when the gun gases come in here and down these tubes, they start working on the head of this piston. And that piston is bearing up against the solid portion of the aircraft. So that means then that the cylinder has to slide down the piston rather than the piston sliding out of the cylinder. The action's the same, it's just that really it's the cylinder that's moving instead of the piston moving. Okay, now then, when the gases come in here initially, the gas passage through these two ports comes right in between the heads of those pistons, so that this piston moves in that direction and this piston moves in this direction. You know, the reason that does is when we've got the tank on the aircraft and it's slid up around this donaker here and these hooks have gone underneath there, we've got to have something in here to keep these hooks open. You know, here's this roller that goes here and a roller right there. The way we keep those hooks in that open position, or where they're holding on to the tank body. See this inclined surface on the top of that?
So that's just running in.
Right. And this thing sits right inside here, just like that. Now the way that thing gets jerked out of there, so that these hooks can collapse and allow the store to separate, is when these gases come in here and separate this thing. This gas blows this thing back in this direction, which jerks this thing out from between those two rollers, and the big piston starts thrusting, and it's thrusting right against this face here, which goes down into this big pin and into this thread in the ship structure. That's what gives you your separation force then, forcing the tank and the aircraft apart. Now then, the only other little thing that we have in here is the shear pin I told you about. When we're loading this tank up on the bird, this thing is collapsed. This thing is already setting, you know, this gap, this piston is already setting over here. And the way we force those two hooks to go back in underneath this collar right here is by the access door that was in the bottom of the nose of that tank, reaching up through in this access door here and pushing on the end of that stem. Then we push that long rod up in between those two hooks, which engages those in there, and to keep that in that position, there's a hole right here, and right there's that cotter pin. That's the shear. So that cotter pin is stowing that thing in up position in between these two rollers, which keeps it locked on the bird. So when the gun gases come in here and initially start to operate, they move this piston in this direction, shearing the shear pin, allowing the hooks to collapse to a released position, and then the piston thrusts right against this pad here, driving that thing off the aircraft. So what you had seen there was that. Now then, further back, where that hardback area, or where that 29-inch strip section, you also saw two big stainless steel doors. Well, they weren't as long as my arms. They're about that long. And they had a half lap joint right here in the middle, so that they lapped shut while they were aerodynamically smooth. They were driven to that position by a big torsion spring along either side of the door. Okay, now then, when we're mating this thing up to the ship, those doors have to be pushed open, and they're held open by a pin. We bring the tank up, Those doors fit right down along inside of. I'm looking for the picture. Yeah, right. Those stainless steel doors fit right down inside these fairings right here. So that, and when you're in flight, these fairings are the thing that is fueling the airfoil. The stainless steel doors are sitting right inside here on either side. The fuel connections are made up. That drag and resting load stud is sitting there. The high pressure hoses are hooked up. And when that all is forcefully ejected away, these things immediately snap apart. Everything disconnects. And as that tank slides away, those big doors walk closed. And that spring is so strong, we had to warn the guys. Keep your fingers down. When you pull that release pin out, don't have your hands because the doors will chop here. Those doors, that spring load has to be heavy enough to overcome aerodynamic loads trying to jerk those doors, open and fly. Do you have, or were you given, because in my pictures here, I don't recall seeing any pictures inside the tanks.
No, I don't think I've seen it. I've got some shots of a wooden mock-up of the tank. That's about as close as I've got.
That won't,
yes.
Okay, the best thing then is to, while we're still discussing tanks and tank structure now, bear with me please. Come sit down.
A little bit.
This is one of those ejectors, all assembled, which the advantage is here is that we're looking inside of this unit here. This is the part up here that had to go in between those two rollers on those hooks. Right underneath here is the lip where those two rollers, or where those two hooks latch on to here. This is structurally all one piece because of this big thread here. This is a big steel tube here. Structurally one piece here and here. Here's the release piston then that has to be forcefully exerted in that direction. Right there's where that shear pin goes. This piston then, once the gases get under here, strokes all the way down here until it bottoms out right here. So that our given stroke distance then is from the base of the head of the piston down to the end of the cylinder. That's the total stroke that we make. Let's discuss another thing while we're at this point, because I told you later I'd tell you why this thing was made to swivel back and forth in this direction. Once again, there's two of these on a bird, right? One forward and one aft. And in that picture that we had of the base of the bird, these hooks are always in a fore and aft direction. So the swiveling takes place forward and aft. This big self-aligning bearing right here is what goes into the tank structure, this collar right here. And that's held in the tank structure by a great big nut that comes up and binds that in the tank structure. But again, you can see that that piston can sit there and do that. This whole housing can sit here and do that in that self-aligning ball bearing there. This thing up here in the aircraft can sit here and do this because by virtue of rotating through that hole around this pin here. Now what happens is fueling the X-15. And you're fueling the tanks. You fuel the external tanks themselves. You bring them up to the ship. You've loaded them on the day before. You've had your engine run and test tanks. You've put the whole thing up on the airplane. It's been sitting out in the warm desert air up there, so everything is warm and relaxed. You hit the inside of that tank with your liquid oxygen, your anhydrous ammonia, as cold as it is. All of a sudden, the tank starts puckering, and it pops and groans. Just, you can hear it. It's groaning, and the metal is squealing, and pop, pop, pop. And since the fuel goes down to the bottom of the tank first, then that's the part that shrinks the quickest. And the upper part of the tank is still at ambient air temperature, so the tank ends up being shaped like a weenie. But then as the fuel gets higher and higher in it, the rest of the tank, then pretty soon the tank is setting level. The only thing is that the aircraft is still ambient air temperature, so it's at its original length. The total change between cold tanks and warm bird, and then in flight, once you get the ship launched, your tanks, because of aerodynamic heating, are heating up. They're going back to their old length. Meanwhile, the ship has still got inside the fuel that it's going to use for the next 65 seconds of burn time after the tanks are emptied out. So it's still puckered up. This change is 19/32 of an inch. Well, then that's why we had to have ball joints on the bottoms and up where we met the ship, because these joints are continuously doing these things in a forward and aft direction. But remember that drag and arresting pin I was telling you about? That always remains fixed. That's a tight fitting pin in that tank. It's fastened in that big rigid hardback in the tank, and it's in that structural frame inside the airplane. So that's why they're so. Now then you begin to see the things that you're faced with in design. Why does it get designed that way? That's a good one of them right there.
Are you familiar with the problems that they had with the gear on the A2 after they extended it? Where they had some problems where the gear was extending itself in flight.
Oh yeah,
because of the thermal problems.
What was happening? The release hook, the Ceron release hook, the strut was simply moving so far that Don Harrison, one of the guys' names really was. He's our landing gear. Come on, USLB. Okay, this is the LOX tank. This is the compartment where there was LOX in. Here's the great big fuel transfer line going. See, you have to go clear to the slosh end, because during acceleration all the fuel is sloshing to the back end of the tank. So this is where we're picking up. Here's these ticklers that I told you about on the back. This shows the new housing and the longer tickler whiskers. Here's that blow-off clamp at the back end to release the little dome so that the fuel splashes out the back. Here's the rear thruster sitting back here, the piston that goes up, unlocks the ship. There's that the drag and arresting load hard pin right there. The fuel, or the filling line for the fuel, and here are those helium storage vessels that supply the pressure to empty the tanks, to pressurize these inside, to get the fuel out of these tanks and up into the bird. And here's the recovery compartment at the front end. The drogue chute, its release mechanism for the door, the drogue slug itself that jerks this out of its compartment here, the cylinder, the method of tying the cylinder. No, I'm sorry, that's the fuel transfer record. Yep. Oh, okay. Here's that structure in better detail right here. Here's the forward cylinder, the big nut that secures at the bottom, the ball joint swivel here to allow for the thermal expansion and contraction. The big cable that goes up inside the tank that secures to the drogue chute. So when this drogue chute flies out here, there's a big 12-foot long stainless steel 3/8 diameter cable in the top of this platform right here. The thrusters for kicking off the nose cone. The pin puller that dumps one lead of the parachute so that the big nose chute collapses. That's just another ejector assembly. Well, this is just an artist's perspective of the tank. Drawings. It's kind of neat in here, and then it shows the relationships of some of these things that don't readily stand out in a 3-view drawing. But here's the cartridge generator housings, the stores away switch, the high pressure gas lines coming up to the front thruster, gas lines going all the way back to the rear thruster, the tube that's really a piece of electrical conduit coming back to various signaling devices there on the back end, outboard sway brace, inboard sway brace, the rocket engine right here with the upward facing nozzle right at this point, and the aneroid switch, the altimeter sensing switch that actuates the parachute. This is the drawing that puts that insulating blanket on that LOX tank. That insulation material on the LOX tank is 5/8 of an inch thick. It's a closed cell ethafoam. It's ethylene foam that's on the outside of that. And even, after 3 hours with that liquid oxygen sitting in there, you still walk up. That stuff was such an efficient insulator.
You already had something wet?
We did that at lunchtime, which really wasn't lunchtime. It was 2 o'clock by the time we got back from there.
Charlie, were you? It's not the same.
No, not on his. Well, okay.
I'm cutting out to get more presents for Sunday. I'm ending up by my dad's. He's going to bring me home. I'm going to leave his car in the garage.
When do I see you again?
Well, Tom's going over there to pick up the car.
You didn't answer my original question. Huh?
Why?
The insulating blanket was that ethafoam, but it was so efficient that even after 3 hours soak time, you could walk right up to those tanks, which the skin was only a 16 thick, and put your hand on them. You couldn't feel that minus 300 degrees. Minus 300 degrees. ammonia tank, but really the ammonia tank was even simpler. It was simply full length fuel plus recovery system, because there was no need for the helium pressure vessels in there. We were carrying those in the space and liquid oxygen in the tank. Okay. Did you go by Lopez's or?
That was his first love.
Mine too.
He was gone away from home lots and lots and lots. And they used to call him the mayor of Tonopah.
Which isn't.
In those
Which
days,
isn't a
in
great.
those days,
Yeah.
Tonopah had more dogs than they had people.
Oh, great.
And at night, if you tried to go walking in that town at night, you better carry a flashlight. There was
That bad.
messes everywhere. Every place. People would come into town in those old rickety farm trucks, and dogs pile off the back, and dog fights would take place right smack in the middle of town. All the traffic would stop, and people would just wait until those dogs got through fighting. Nobody'd get out to move the dogs.
Oh no, I don't want to get in the middle of it.
And with, a third of the building's empty because it was an old silver mining town. Silver mines had all run out. To be the mayor of Tonopah was it was just an honor.
It was just
name.
because you spent so much time.
Honor.
He was up there more than he was at the plant.
Yeah.
Was this one among your?
I've got one of those. Yeah.
That was made with one of those presentation models.
Mhm.
There.
Yeah. Too bad they don't have any shots like that in flight. That clear and everything in flight.
Yeah, but how are you going to get there?
Yeah, true. They had to have a chase plane at the right place down there so it could snap some shots
Well,
as it went by or something.
Usually, 1 second to launch, while one guy would kick in the afterburner and get
Yeah.
out there just as far as he could. The other guy would stay right by the bird through the initial drop, because that's the most critical time.
Oh, yeah.
Initial drop and light up
Get the light off.
and get going. And then that other guy would get out there just as far as he could, but he'd go past him so fast.
Oh, yeah.
It was ridiculous. But anyhow, this is one of the first things that we made long before anything else was done, because everybody wanted to know what it was going to look like.
Yeah.
So then Gene Boswell shot a bunch of these pictures, and we released them to everybody. But it was built with one of those models, those presentation models there. And those things aren't really to scale.
Yeah.
You start, I know what all the ship's dimensions are.
Yeah.
And so I sat down to figure out just where all the mistakes are on that
Oh,
model,
yeah.
and where all the mistakes are on the Revell model kits.
Oh,
They're-
yes. That's
they're-
a fun one.
Yeah, there are a lot of them.
Unfortunately, the Revell is the only halfway decent one that ever came out. Did you ever see the Aurora model that came out? It was based on a drawing that was released really early in the program before anybody knew what it was going to look like, and it is so totally off. But they still produced it by that. It was a drawing that was originally produced in Popular Mechanics or something, I think. And it was bad. It was really bad.
That's got one scale on part of it, another
Yeah.
scale on another part of it, another scale someplace else.
Oh. They don't always put me. They always put the tail number, whatever, way up on top too. They don't even put the NASA up there.
Yeah.
This as far as the markings go.
Yeah.
Yeah, I reworked a.
One of those drawings there is the markings drawing.
Oh yeah. Oh, that'd be great. Yeah, I'd love to take a close look at all that stuff. I say a friend of mine is an excellent technical illustrator. He wants to do lots of drawings of how everything is. Yeah, I took one of the Revell kits and modified it into the A2.
Well, you made
And
a dash 2 on it.
oh yes, it took quite a while, but it was fun. It was
Did you
worth
put
it.
in the stretch too? The
Oh yeah.
20
Yeah, I had the stretch, has the tankage on the back, and I put the long gear on the gear. You have to throw away the gear and start from scratch on it. And it's in the version. It's after a flight. It's sitting on the lake bed.
Okay, so it doesn't have.
No, it doesn't have the tanks on there.
Doesn't have tanks.
Yeah, and I took it to an IPMS meeting over here, and I got a first place out of it, which was
Great.
pretty neat. So that made me feel real good. So I've got that sitting on my shelf now. the original Orville. Oh. One of these days we're going to come up with a good model.
Pictures like that are just pictures sitting up there at the desert. This happens to have the mock-up of one of the
Ramjet?
yeah,
Yeah.
Ramjets hanging.
Oh yeah. Yeah, I think I've got some shots that are probably taken the same day. What is this? I've noticed that on the one at the Air Force Museum. This door that's in the middle of the nose gear door. What is that
it's
for?
an access so you can get up there to lock that mechanism prior to flying.
Okay. That's right, because
Yeah,
it was a
maybe
hand.
one of Don's drawings. I went through those drawings pretty fast.
Oh, no.
Whoops.
Okay, I was wondering what that was. Now, does that door, I noticed when it's sitting in the Air Force Museum, the main door is down and then that door is hanging open. Did it open also during, or was it always latched shut when the gear came down, or do you know?
Right now, I don't know.
Okay.
Let's see Don's drawing. But I worked on when we had the trouble with those releases due to thermal expansion thing. Then Don had to redesign it. Well, right then tanks we weren't doing a heck of a lot. So Jim Dole says, Robbie, you help Don redesign that door. So we got into the monkey motions of that hand thing and what we had to do in that little access door. But boy, right now that's for me.
Oh, yes.
Here's two different sets of markings drawings. Well, this is for the B-15. Oh,
It's like B1.
that's the B-1.
Yeah.
B-1 drawing fit in here. I got a lot of stuff on B1s too.
Yeah.
Except I don't have any classified stuff. But I got a huge picture library on B1 because I spent so many years on that too. Yeah, here's the markings drawings, and it shows all the markings drawings on all the hatches too. Where they had the interface along how each door was marked. Yeah, this is the -2 bird.
Yeah. Yeah. Another question on the -2. If I can go back to the other one. This one. Okay, the fairing along the side on the original one, it cut off right at the back of here, but it was extended back. Why was that extended? Why was the fairing extended? Do you know? Okay.
You're going to have to check with one of
Okay.
somebody else that.
Yeah.
This is the right-hand side, and these were the left-hand side markings. Wing markings.
That's something we're really looking for. The drawings we have now are just the side view. We have nothing that shows the top view, so we don't have the actual plan form of the wing.
Oh, yeah.
That'd be great. Oh, and bottom too. Good.
Yeah.
Oh, yeah.
John's dead now. John Jarrett. And I have to edit that.
What's his name again?
John Jarrett.
With a J?
Yeah.
Jarrett.
I made this up too for you.
Oh, this is great.
Now then, that's all of us that were left in the group at the end of the project.
Mm-hmm.
In other words, you get this tremendous influx of a lot of people right at the initial phases. And then if suddenly there's a change, then meanwhile the group drops back to normal operating level. Then something else will come along, you get a few more people in, or something special goes on, and you have to borrow. Say you need a few hydraulics engineers, you borrow them out of somebody else's hydraulics group. But it's still an all intercompany thing.
Oh, yeah.
But at the end of the program, this is all of us that were left, and that's John standing right there next to myself. Now, a lot of these early drawings you're going to find will have John's name on them. John is a real top-notch design engineer, and basically fuselage structure, total overall aircraft structure. He's very good at it. But I've tried to name almost all the guys in the group, except the only two I didn't get on there were these two guys. I know them, and I just cannot think of their names yet. I should know his name so well because you're aware that I'm collecting beetles too.
Yeah.
And one year he brought me in a beetle, and so Robbie went out to my wood box last night to get some wood for the fireplace, and said this great big, and he showed it to me. And it was a real rare thing that we have it's only found in the coastal ranges and along the westerly slopes of the Sierras. We have 31 species in the entire genus. It's the only place in the world they're found. I went up and I spent 2 winters at John's house looking for those things. I'm saying John right now, but is it? Maybe his name is John what then? So I went in when I was thinking up all these names yesterday. I went in there to look at that beetle to see if I had put his name on the label. I didn't. But anyhow, these are all the guys that were in the group. Now the other guy,
the girl here looks like a Navy uniform or something.
no, she just dressed up.
Oh, okay.
She's just our secretary.
Yeah.
But the other guy whose name and address I'm going to give you today is going to be Harry Shapiro. Harry's got lots of stuff. He was a young fellow just out of college when the X-15 program first started, and it was his first job, and he was there clear through the end of it. He's the electrical engineer for the group. Harry's thesis to get his degree in college, he did Scott Crossfield's first flight. That's what he wrote his paper. And then he came to work and worked in the X-15 project group for something like 9 years. Total length of the program. Those were the flights, the Dash 181, Dash 283, and Ship 3, 65 flights at the time that Major Adams was going. But that's the way the group stood. While we've got it there, let's talk about it. Gene Miller and Harry Shapiro and Hank Shippen. Those three guys are all electricians. John Jarrett is a structural design man. Myself was external stores and explosive devices. Al Dowdy is a stress engineer. He's a stress engineer supervisor. This man has a fantastic knowledge in that head, and he can think on his feet just like that. If something would go wrong in a flight, or something fail, that son of a gun could tell you a load had failed before you could read the instrumentation data. He was so unique at that kind of thing. Henry Louis is power plant. He and Phil Stockwell and Johnny Clark are all power plant people, engines. Don Harrison and Earl Harrison, who worked with him earlier, by the time this picture was taken, Earl was already over in preliminary design in B1, doing landing gear on the B1. But Don started with Earl initially on the X-15 and continued all the way through. This is the guy that, whether it was the skids on the back end or the nose gear or that nose wheel gear door, why Don Harrison's the guy. Milt Schoenfeld was a supervisor of the group. Pete Paxson back here is our thermodynamics man. He did all the ablative covering on the ship, the ablative covering on the tanks. Ablative covering is
Mm-hmm.
the stuff that burns away at constant
Yeah.
temperature.
The stuff that Martin built.
Okay. Any of the skin sections, any of the structural joints where we had failures due to thermal problems in the joint, expansion, contraction, parts getting soft because they're getting mushy because they were too hot, those kind of things. Those were always Pete Paxman's problem, and to some extent Bob Johnson. Pete worked for Bob, and Elmer is hydraulics. Elmer did us. Jim Dole, right here, was group leader. Over Milt Schoenfeld was just one of the local group supervisors, and Jim Dole was over him. Earl Sykes had charge of the X-15 after Howard Evans left and went to B1. Howard Evans was the chief project engineer for a long time. And then after we started the B1 and Howard Evans, that's another guy that's a fantastic designer. He started designing for North American back in the days of the P-51. But they required Howard Evans' services in B1, so then we got Earl Sykes. Earl Sykes wasn't a long time X-15 man, but he was from management level. And Earl Kavicki here was in power plant with Henry Louis